Hello everyone. Recently, I have joined a reading group for generative AI at my master's here in Montreal. And as part of that reading group, I have been going through some pivotal research papers in generative AI, especially large language models, vision language models, agentic workflows, and all that. So, I decided why not use one of these presentations and probably make it a recurring segment where I discuss these pivotal research papers through some visuals, through a presentation to help you understand how these research papers work and how they might be used to inspire your next project. So let us take a look at this paper. Video-LLaMA model has been introduced in a paper called An Instruction-Tuned Audio-Visual Language Model for Video Understanding. So, trying to understand why this model exists, at the time of its launch, there were a bunch of vision transformers available like Flamingo, Blip2, ImageBind, Lava, mini GPTs, and audio-only transformers like AudioGPT. But there was a serious lack of video transformers which are able to understand videos as a whole without relying on external tools to understand visual and auditory dataset. And that's what they have tried to do over here by introducing the model. They have introduced a multi-modal model capable of understanding videos, specifically temporal dynamics and the audio-visual integration that is involved in such video comprehension tasks. They do so by introducing an end-to-end comprehension, which means that no external tools for vision or auditory comprehension has been used. And finally, they do it so by a multi-branch cross-modal training. It's a dual branch architecture to train visual and audio language in separate branches and through just one pipeline. So basically, the video is divided into image frames which are first fed into the visual encoder. This transformer includes a VIT that is generating detailed image features and a Q-former which is using query tokens to capture the most important features to create query embeddings. This particular step has been greatly inspired from Blip2 architecture, which you can see later on as well. Once we have these most important features that have been captured by the Q-former, they are collected into a joint video embedding frame, which you can see over here. It is denoted by the larger triangle holding all the light colored columns. These columns are represented by Vi belonging to Kf into Df, where Kf is the number of image embeddings and Df is the dimensions of each embedding vector. Now, once we have the video embeddings, temporal information about individual frames in reference to the other frames around it is introduced in the model by positional embeddings. This positional embedding layer ensures that the video Q-former is later able to understand the relationships of individual frames with and around whatever frames they are. The video Q-former presents a condensed video embedding which is taken from the joint video embedding plus temporal information and feeds it directly into the linear layer. The condensed video embedding that I'm mentioning over here are the darker squares that we see over here, which are feeding into the linear layer. The linear layer is then finally transforming the video embeddings into video query tokens for the LLMs. That is going to be Vicuna for our case, which we'll get to in a second. Now, the architecture is working hand in hand with the audio language branch as well. The audio language branch, quite similar to the video language branch, is a pre-trained audio encoder which is being fed M segments of 2 seconds each, which have been converted into spectrograms. Each spectrogram represents the audio of every 2 seconds. Each spectrogram is mapped in dense vectors by the audio encoder. Similar to each image, each audio segment also receives a temporal address. Point to be noted over here, this temporal address is not the same as the image temporal address, but it does help in understanding the sequence in which these data points are occurring in the particular video. And once we have the audio segment with the temporal address attached to it, it is passed through the audio Q-former, which, similar to how the image encoder Q-former was working, presents us condensed audio tokens, which are then fed into the final Vicuna model. Now, to understand how this architecture is working towards giving us a good performance and understanding video, let us see how the training itself has taken place. The vision language training is divided into two steps. One is pre-training and the second is instruction tuning. The stage 1 occurs by using a video captioning dataset from WebVid 2 million, which contains video to text generation captions. And finally, static visual captions, which have 595,000 image caption combos. Here they are using a video captioning dataset, WebVid 2 million, video to text generation, and a static visual caption dataset, CC595K image caption. For those who are curious, CC595K is the dataset that Lava was trained upon. And moving on to the second stage, the instruction tuning. The second stage is where the model is understanding how to answer questions regarding a particular video. This has been done by using a video-based conversation dataset from MiniGPT-4 and image instruction dataset from Lava. And finally, a video instruction dataset from VideoChat. We will be talking about these models later on. But what you need to understand is that these are good data sets that are describing particular questions asked from a video. Now, for the audio language training, this is where it gets complicated. At the time of the model training and the introduction, there was no audio text aligned data available. So they have decided to train the model using visual text data. That's where it gets interesting. How did they use visual text data? Well, the audio encoder that they are using is image bind audio encoder, which is a multi-modal serving 6 modalities. So what they try to do is, by training the visual aspect of the image bind model, they are trying to also enrich the shared embedding space that all the modalities have in image bind, which means by understanding images, it will be able to understand how audio is working as well. And secondly, they have used a small secondary data set of audio to text generation. Now finally, the experiments that they have shown are video with background sounds, where you can see that the model is able to understand the audio from a video and is able to answer questions regarding that. The descriptions generated in the case of videos with sound are more concise, as the model is able to narrow down its further embedding space that have been generated by the video and the audio encoders. And you can see that when a video is presented without a background sound, it is solely answering the question on the basis of what the video encoder told it. So it can be a larger sentence. The video on right quite shows how good it is in understanding temporal data, wherein when asked which direction the ship is going, the model is correctly able to tell where the ship is going. And finally, the static images, where it is performing as expected because it is using a combination of Blip2 and Vicuna, wherein it doesn't really require any of the video or the audio encoding parts. Now, the discussions that were presented by the paper and have been true according to time, are that the lack of audio text data makes the model hallucinate a lot. As you can see in the video on left over here, that the man is closing the door, not necessarily a dog barking in the house. But it is not able to understand the noise made by the door was the noise actually, not the dog barking. And finally, the handling longer videos is very expensive, as you are increasing the number of columns, as you increase the number of frames. Most evaluations done on this model have been done on 8 frames. Model often hallucinates a lot because of the frozen encoders, especially in the video pipeline, where VIT taken from blip is a rather old encoder which will not have most of the latest understanding of code or different scenarios. And that's where I leave you. So please let me know what you think about this model. If you would like me to discuss any other such models, any other research papers, please let me know down in the comments. And until then, keep your models fed and your code bug free.